Hi, this is Professor Cummings, and I wanted to do another video here, but haven't had one in a while. Been doing most of my classes virtually and just haven't taken the time to make an actual video for the YouTube channel. But there's a video that I've been meaning to make for a while, meaning a couple of semesters now, that was around the joining process. I don't have many of them, even though I do cover this in my manufacturing classes. So what I want to do is, this is a video on joining, like I said, but what I would need to start off with is this picture you see in front of you, which is a phase diagram. Now, this is a very generic phase diagram. I randomly grabbed it because it's for its simplicity. So it's not going to be a focus on the materials down here on either side, but I do want you to pay attention to a few things about it. Number one, that the x-axis is the percent of particular alloy, that the y-axis is the temperature, right? Now, down at the bottom below this particular line, known as the solidus, everything is solid metal. So we've got the lower case here of solid metal. We've got the upper temperature here, which is the molten metal. And these two lines, again, I already said this was the solidus line. This is the liquidus line, where things transition into a molten metal. And if you were to follow, the way you would use this phase diagram is if you were to take a particular alloy, whatever that is, whatever percent alloy it is, and you were to elevate the temperature, you would actually cross the solidus line as you heat up the metal. You would go through what is known as the crystallization or recrystallization stage, or the mushy zone, where there is a portion of liquid and solid within the crystal structure. You would go through this crystallization zone and into molten metal, right? So, metal has those stages: a solid, a molten, a liquid state, and in the middle there's something called the recrystallization state. Now, I want to focus in on this recrystallization state because it's very important as far as how joining works. So here, that's the recrystallization state of metal. So a lot of things happen in this recrystallization state. One is, this is the state you bring metal to when you want to start doing forging. It's also where you want to start doing heat treating. You can actually change the crystal structure, hence the name recrystallization. It's where you can actually start to promote crystal growth. And basically it's like hitting the reset button in a lot of cases for metal where the crystals have been deformed or damaged. It's also a way that you can actually, depending on how you cool the metal down, or what environment it's in, that you can actually change some of the characteristics of the metal. So this recrystallization state, let's give it the formal definition. A process by which deformed grains are replaced by a new set of defect-free grains that nucleate and grow until the original grains have been entirely consumed. Right? So what happens in recrystallization, it helps dictate the crystal structure that the metal you're dealing with is. It can leave the metal softer, more ductile, or it can leave it hard and brittle, depending on how, a few things about how you handle that material in that recrystallization state. So the quality of that crystal structure is a function of things like time, a function of things such as the temperature, of actually getting it to the recrystallization state, and then the environment. You can actually have a dramatic change on the crystal structure depending on what type of environment you put it in. Now, all these things have a major impact on joining processes. And it's important because they can actually have a very detrimental effect on your joining, or they can actually have a very positive effect on your joining process. Now, these are just images of, what happens in the recrystallization. Here you can see the grain growth, crystals actually starting and actually form into an actual grain, so that starts with a dendrite, creates crystal. I think I have another video where I actually show you that on my materials playlist, where we actually discuss this, and actually forms into a grain. Now, if you have metal that's actually been, work hardened, the crystals have been deformed, you can actually go through the recrystallization state, bringing it up to a certain temperature, depending on whatever the alloy is, and the crystals will start to actually reform themselves, kind of like what the original definition says. So these are all things that are important to understand because they become an inherent part of the joining process, primarily because joining, it requires high temperatures, or usually there's some sort of temperature change, as well as the fact that there's some influences that are going on in the environment. When you're actually doing a welding, different types of joining, welding types of applications, as well as the time that you actually take the material up to that state. So let's look at how these, beyond recrystallization, let's look at how the phase diagram plays into, joining metal. So again, depending on the type of process you're talking about, joining utilizes either the solid state of metal, the molten state, or it actually goes straight to the recrystallization state of a particular material. So you have fusion welding. It's probably the one that most people who think about welding, that's the first image that conjures up, is somebody actually, what the thumbnail is going to look like under this video. Somebody actually welding a metal with a torch or some sort of a welding stick, and you're seeing all the sparks fly off. That's the metal being brought up to the molten state. Fusion metal actually requires that the metal is brought up to the molten state. It recoalesces and forms a joint. You got solid state welding, which goes only up to the recrystallization state. The material is joined in the recrystallization. So what you're looking at here in this particular diagram is joined metal that simply is joined because it was recrystallized. And that's the weld center zone, WCZ. So this metal was never brought to the molten state, but yet it was still actually, joined through the solid state welding process. And then the lowest temperature version of this is brazing and soldering. And these are both very low temperature state material or low joining processes. The base metal in these particular applications, unlike fusion welding and solid state welding, the base metal is never brought out of the solid state. So it never actually reaches the solidus line in the phase diagram. It's all done with the filler material. So the filler material is brought to the molten state, and that's what causes the joining of the two base metals. So if we're to look at these different types of processes, here at the top you've got fusion, and you've got solid state and brazing and soldering. This diagram is actually specifically about brazing, but they're very similar processes. And where they land on the phase diagram. So you can see that the fusion welding actually has molten metal. Actually brings the metal up to a molten temperature, and it cools down, and the crystals reform, and actually causes you to have your joint. Here you're only brought up to the recrystallization state. What also gets called the mushy zone. Sometimes it's called the forging temperature, and this is where you actually recrystallize your material, and the grain growth causes the bond. And then you're in the solid state, solid level. What you have is the base metal never actually goes beyond the solidus line, our solidus point and solidus line, and the molten metal is based around the filler material, which basically fills in the clearance. So let's go to a little more detail of the three of these. So if we look at fusion welding, fusion welding takes place up in the molten state of metal. So you can see here, just from this diagram, we got all kinds of information here. What we have here is, your temperature is being brought up past this, whatever this liquidus line happens to be, depending on the alloy. The temperature actually reaches a liquid state. So you got this molten pool. And as you travel, you're actually traveling with your heat source, your electrode, going in that direction. That molten pool, it melts the metal, travels across, and the metal starts to recrystallize behind. Now, if through the material videos, you have two different types of ways that crystals form. If you cool things down slowly, you end up with columnar grains. This means they're losing heat more slowly from the heat source. But the quick, cooling, very rapid cooling, usually ends up with equiax grains. So these are the smaller grains that you're seeing here, that are trailing the electrode. And what you're seeing up here is just defining the entire mushy zone of the metal. So this means that, you're still cooling down and you're in the recrystallization. So the crystal is actually growing. So you can see you got the entire phase diagram happening here. So this could also be called recrystallization. So you got all sorts of different processes or all sorts of different phases of the phase diagram, both within, the electrode region and following behind where the crystals actually start to reform. And then as you travel away from the material, in these directions here, the effect that you're having on the base metal, beyond just where the weld joint is taking place. And that's what's known as the heat affected zone. What that is, that's the material that is actually still, it might not be brought up to the molten state. It still may actually be in this recrystallization state, may in the zone of the material, simply because the temperature is dropping the further away you get from this source of heat, and then further into the solid state. So you got this entire zone of material that's going to be affected by the heat, but it wasn't necessarily the target of the weld. So when we look at this, just kind of give a little summary of fusion welding. The base metal reaches the molten state. As you can see here, the base metal, because of some sort of electrodes, reaches to the molten state. The heat affected zone, the non-molten metal, is affected, and is similar to sort of a heat treating process. Now, it can be prone to brittleness, unless it's protected by slag. What happens is the slag, which is essentially the impurities that's in the metal, they might have been absorbed in this metal, or may have come from some of the electrode, or just the surrounding air. If there wasn't a shield gas used, can actually start to form a crust on top of the metal. This slows down the cooling process and can actually help your grains. It can actually make the material less brittle and more ductile. So again, it helps with those columnar grains. Again, that's, if you have the slag on there and you leave it on the appropriate amount of time, you can have an annealing effect. And typically, there are exceptions to this when we start talking about major things like bridge building and shipbuilding. But typically, this fusion welding has less expensive, and I say relatively less expensive, maybe is a better word, equipment that's used for compared to things like solid state type welding. So it's relatively less expensive and much simpler equipment. Now, when we talk about solid state welding, again, you are only staying in the recrystallization state. So just in this region, you never go to a molten state of metal. Sometimes you might hear this called the forging state or forging temperature. So you only stay here. And what's happening is you are actually starting grain growth from two separate materials and forming your bond. And here is that weld center zone. What you'll also notice is that your heat affected zone is actually very, very tiny. The temperature didn't go nearly as high. Most of it was focused in this area where it was recrystallized. Anything else was still in the solidest state. There may have been some temperature migration up here, but it's a very, very minimal heat affected zone in solid state. And here we got the parent material. Now there's a few things to keep in mind about solid state welding that is very important. You'll notice a couple of things. Number one, that you need some sort of applied force between the two materials, bringing them together. You need some sort of relative motion. That's where that oscillation comes from. And there's different types of solid state processes that depend totally on friction. So you apply a force, bring in some sort of a relative motion. And in some cases, or a lot of cases, you might have an outside heat source, you know, an electrical current or some sort of electrical resistance or some other type of heat source. And that's what brings you to your bond. But at no point in time does it go to a molten state. So the metal will actually be brought up, and, you know, with that relative movement, you have some recrystallization. Now, another thing about this movement, you end up with a phenomenon known as dynamic recrystallization. Now, dynamic crystallization. Dynamic crystallization, what happens there is that you're actually crystallizing because of that motion. You know, so this is where you see with certain processes known as friction welding, where you're actually moving the two parts around each other, and that's what causes the bond to take place. So the base material, just to sum this out, base material, you know, only reaches the recrystallization stage, does not go into the molten state. It requires some sort of force, some sort of heat source, and some sort of relative motion. You know, and that's where you get your dynamic crystallization that creates your bond. You know, you have a much smaller heat affected zone. And last, the equipment for friction welding, or excuse me, solid state welding, typically is much more expensive. Typically, it's usually a fairly expensive process to do that. Yeah, there might be some exceptions to that, but by and large, it's usually a more expensive process. Now, brazing is different from the others. This is usually a lower temperature process, brazing and soldering. You know, they're fairly low temperature processes. The base metal never comes beyond the solid state, never crosses the solidus line. It stays down in this region. What does actually get heated up to the point of molten is the filler material. Now, when you bring things in for brazing and soldering, there's a certain amount of clearance that you expect to have between the two different materials. So what happens is that molten filler, the molten brazing material or soldering material, is drawn into the clearances through a capillary action. And it's that capillary action that draws you in, creates your bond, and, you know, it's actually what sets you up. And again, this is usually a much lower temperature process than welding of any kind. Now, one of the downsides of this is the need to have that material surface is very, very clean. Without that, you can't have that adhesion with the filler material. So any sort of oils, any sort of oxides on the surface should be cleaned off before you do any of your brazing or soldering. So I'll give you some summary here. You know, the base metal, again, remains totally solid. The filler material is where you're getting your bond. There's a capillary action that draws the filler material into the clearances. You know, it's a much lower temperature process. As you can see, if it's in the solid state, it stays much lower temperature than the other two. And surface treatment is crucial to bonding. So that's as far as I wanted to go with these just basics on joining and with the differences between these processes on. So go ahead and like the video, you know, subscribe to this channel, because I do plan on putting out more on this particular topic. This is one that I've neglected. And, you know, share the video around. You know, I know that within this day of a lot more virtual teaching, I think this might actually be a little more helpful to some people to have this type of material going around. And I'll talk to you guys later.